All right. So we talked about quantitative variables and qualitative variables before. And when we were talking about the qualitative variables, we said that they could be nominal, which means that we were just naming the things, or ordinal, which meant that they actually went in order. There's two more pieces that actually go with the quantitative scale. With the quantitative, we said that we could have discrete things, which, let me go back to that actual handout. We had discrete, and we said that discrete was things that, like, we could count those numbers. There was a finite number of those numbers because we could say, like, shoe sizes or something only come in 7, 7.5, 8, 9, 10, 10.5, but you can't have like 10.527 as a shoe size. So discrete means that there's a finite number of the values that it can take on. Continuous typically happened with a measurement. And with the measurements, it could be any value. So it could be like a weight. If we weigh somebody and you have a good enough scale, someone actually could weigh 100.0725 pounds if you had a really good scale that kept going out to those decimal places. So we said those ones were continuous. There's two more pieces that go with the quantitative. One of them is called the interval scale, and one of them is called the ratio scale. On the interval scale, which, let me just go back to the top part. The interval and ratio scales both fall under our continuous measurement scales, but they have some slight differences here. With the interval scale, there's equal intervals between the values, but there's not really a true zero. And here's what I mean by that. If we were to look at IQ scores, remember last time I said an average IQ score was 100. And if you have over 100, that's considered above average IQ. And if it's below 100, we consider that a below average IQ. If someone got a 0 on the IQ test, that doesn't mean they have no intelligence. That 0 doesn't mean anything. In the same way that if we did temperature, you can have a 0-degree day outside, not usually in California, but other places. It could be 0 degrees outside, but that doesn't mean there's no temperature. Like the 0 is actually a value that's just sort of dividing out the positive numbers from the negative numbers, but the 0 doesn't mean a complete lack of value. And so when that's the case, you're on the interval scale. The ratio scale actually has a true 0 value. And so some examples of that would be height or time. If I actually am measuring someone and I say that you're 0 feet tall, that actually means that you have no height, right? Or if I've got a stopwatch or something and 0 seconds have passed, I mean no time has passed. So the 0 actually means something in that case. Whereas a 0 on a thermometer, it means something, but it's not a true 0 value. It's just the dividing line between the positive numbers and the negative numbers. So if she gives you homework type questions, I'm talking about Dr. Whitener. I know I have some people who are in the other class, but Dr. Whitener's class, if she gives you a homework question and you're having to identify if it's part of the interval or the ratio scale, what you want to think about in the question is, what does the 0 mean in this problem? And if the 0 is meaningful, like the 0 actually means a complete lack of the thing. So 0 time has passed, or you have 0 height, then you're on the ratio scale. If the 0 is just sort of a thing that divides the positive numbers and the negative numbers, but it doesn't actually mean a complete lack of the thing, then you're on the interval scale. Is that okay? Hold on to this example sheet because it's kind of the easiest way to tell the difference between them, because those are kind of the examples that come up all the time. Anybody not get the handout? Cool, all right. Oh, well. I'm trying to do a good job of making on the table, so if you come in after I start, they can still be able to grab a handout. Okay. Go ahead and flip your handout over now. We're gonna do something that I think probably came up during Dr. Whitener's class today. We'll see. Did you guys talk about relative frequency histograms? Okay. So I'm assuming she showed you pictures of different charts. Did you see like pie charts, circle charts, and then bar graphs, and then line graphs and stuff? Okay. Those are different ways that we can organize different types of data. One of the things that comes up a lot in the homework questions is frequency histograms and relative frequency histograms. And they're slightly different than each other. And so I want to kind of talk you through the difference between them. Okay. So we're going to pretend like you work at a library. And at the library, they're trying to determine how many books is a normal amount of books for people to read in a month. So they're taking kind of a poll. And so they're seeing how many people read 2 books in a month, how many people read 3 books in a month, how many people read 4 books in a month, 5 books in a month, and 6 books in a month. Okay. And so when they asked, only one person said they read 2 books in the month. Okay. When they asked, 3 people said they read 3 books in a month. 5 people said they read 4 books in a month. 2 people said they read 5 books in a month. And 1 person said they read 6 books in a month. 6 books in a month is a lot of books. So that person loves reading a lot of books, right? What this is a table of frequencies. The frequencies just tell you how many people or things did these things that were in the first column. So off to the side here, you could have had colors or something, and it could have been like, you got a bag of M&Ms, and I could have put the colors there, and then been like, put down how many of those things. The frequency is how many did the thing. In this case, I didn't have colors, I actually had numbers, but these numbers are not frequencies. They're describing how many books they read in a month. So in statistics, reading, the like actual labels on things ends up being super important, because sometimes the question will be asking you to talk about something that looks like it's numerical, but it's really just categorizing things. So we're really in that first column just categorizing how many books people are reading, but this is telling you how many people did those things. Okay. This is called a frequency table, and you have a frequency histogram right below. This data matches the stuff in the chart. So you'll see that we only had 1 person read 2 books and 1 person read 6 books. If you look at our picture, off to the side, these are the number of people. 1 person read 2 books and 1 person read 6 books. It's matching the data in the chart. If I go to my highest one, the highest one was 5 people read 4 books. So when I go to 4 down here on the bottom, 4 is the number of books. This needs to go up to a height of 5. And it does. So all of that information matched the chart that we had at the top. Okay. This is called a frequency histogram. A relative frequency histogram, however, takes into account the number of people that you asked this question. So if I go back to this table, we asked 4 plus 5 is 9, plus 2 is 11, plus 1 is 12. We asked 12 people how many books they read. So what I'm going to go ahead down here is write 12 people total. And I'm going to make myself another column in this chart. And what I'm going to title this column is the relative frequency. The relative frequencies are going to be either fractions or the decimal equivalents of those fractions. And all they're going to do is they're going to have this column as the numerator and 12 as the denominator. So the relative frequency of people who read 2 books in a month is 1/12. The relative frequency of people who read 3 books in a month is 3/12. Relative frequency of people who read 4 books in a month is 5/12. 5 books in a month is 2/12. And 6 books in a month is 1/12. So when you're doing relative frequencies, you just have to figure out how many people or how many things you asked total. And that's going to become your denominator. And then all of these things are just your numerators. If you were to add them all up, these fractions have to add up to 1. So if I add 1 plus 3 plus 5 plus 2 plus 1, I get 12. And 12 over 12 will give you back 1. So if you've done it correctly, it should always add back up to 1. Okay. I'm going to go ahead and find the decimal equivalents of these things because it's going to help me actually make my chart or my graph. So 1/12 is 1 divided by 12. That's 0.083. Okay. 3/12 is 3 divided by 12. That's 0.25. I should put a 0 in front just for consistency here. Okay. 5/12 is 5 divided by 12. That's 0.417 if I round it. 2/12 is 2 divided by 12. That's 0.167 if I round it. And then 1/12 we already did. That's 0.083 again. And I did that so that I can make another chart that looks an awful lot like this one, but the labels are going to be different. So I'm going to go ahead and draw my axes in. But instead of writing frequency along the side like we did on this one, I'm going to write relative frequency along the side. Along the bottom, you still have books read. So that label didn't change. And I'm still going to have the numbers 2, 3, 4, 5, and 6 along the bottom, because that's, again, number of books read. But then going the other direction on the y-axis, instead of putting 1, 2, 3, 4, and 5, I'm going to put decimals. I'm going to put 0.1, 0.2, 0.3, 0.4, and 0.5. And so we got to go back and look at our numbers for 2 books. That's 0.083. That's a little less than 0.1. So I'm not going to go quite all the way up to 0.1 when I make my bar, but I'll get close. So like maybe right about here. And then for 3 books, we had 0.25. So 0.25, that's going to be right between the 0.2 and the 0.3. I'm going to go exactly in the middle, and that's going to be the height of that bar. So just like that. Okay. For 4, we said we had 0.417. So I'm going to go a little bit past the 0.4 for the height. For 5, we said 0.167. So 0.167 is going to be a little bit past halfway point between 0.1 and 0.2. So I'll maybe go like right here. And then for 6, it's going to be exactly the same height as the one for 2. And there we go. So how this looks has the same shape as this distribution. Your frequency histograms and your relative frequency histograms are going to have exactly the same shape. That part's not going to change. But what does change is the units along the y-axis. Here, these are going to be whole numbers. So these are the frequencies. And here, these are going to be the relative frequencies. It's going to be the decimal numbers that we had in the last column. But they should have the same shape. Is that okay? We're going to use those to help us answer a couple of questions on here. What proportion of the readers in the sample read between 2 and 3 books per month? This is probably easier done from the chart than it is from the graph, just because our graph has some kind of crazy decimals on it. So between 2 books per month and 3 books per month, that's the first 2 rows here. The proportion is going to be 1/12 plus 3/12. Is that okay? So I'm going to say 1/12 plus 3/12. Since the denominators are the same, we just keep it 12 and then we add the numerator. So this is going to be 4/12. 4/12 is the same thing as 1/3 if I simplify that fraction. You don't have to simplify the fractions. 4/12 is perfectly okay. But 1/3, you might know what the decimal equivalent of 1/3 is. It's 0.333333 forever. So as far as a percentage would go, or a decimal would go, we'd say that 0.3 forever. Or in terms of a percentage, that would be about 33.3%. Those are all valid ways for you to give the proportion. So you could give the proportion as 4/12, that would be okay. You could give the proportion as 1/3, that would be okay. You could write it as the decimal, or you could give the percentage. Those are all equivalent to each other. They're all okay. And the reason I say that is that sometimes on the homework problem, she might switch. So sometimes she might do a decimal and sometimes she might do a percent. You'd be like, what? And it's okay. They mean the same thing. Questions on that? Yeah.
Do you know if I'm expected to know how to put them into decimal form or percentage form, or should I get access to a calculator?
So what I have heard, I can't watch your guys' lecture, so I don't know for sure, but you'll have to verify for me. I've heard you can't use a calculator on your tests. Did she say that?
You can use a scientific calculator.
She lets you use a scientific calculator on the test?
I think so.
Cool. If she lets you use a scientific calculator, then all you have to do is take the numerator and divide it by the denominator, and that's going to give you the decimal equivalent. So if you're allowed to do that, that's cool. If she's not letting you use a calculator, or she's not requiring you to use the calculator, normally she's got like parts in the problem where she'll tell you to put like a little star, and that would be where you would normally plug it into the calculator. So you just go ahead and leave it at the 1/3 or at the 4/12, and then put like a little star. And then she would assume that you would then use the calculator to do the thing. But if you get a scientific calculator, to find the percentage, you just take the numerator and you divide it by the denominator. Good question. Other questions? What proportion of the readers in the sample read fewer than 6 books per month? Fewer than 6 books means we can't include the 6, but I can include everything else. You could take 2/12 plus 5/12 plus 3/12 plus 1/12 and add those all up, right? But what did I say about all of these fractions? What do they always have to add up to? They always have to add back up to 1, right? So if I'm saying you're going to use everything except for the 1/12, what's 1 minus 1/12? 11/12. So you actually don't have to do the adding. You could also subtract from 1 if you want. There's 2 ways you could do this. So I'm going to write both. They're both valid. You could either take 1 and subtract the 1/12. 1 is the same thing as 12/12. So 12/12 minus 1/12 would equal 11/12. That's one way to do it. Or, sorry, you couldn't see that. Or you can take the 1/12 that we got for the people who read 2 books in a month, plus the 3/12 for the people who read 3 books in a month, plus the 5/12 for the people who read 4 books in a month, plus the 2/12 for the people who read 5 books in a month. And if we do that, your numerator is going to be 4 plus 5 is 9 plus 2 more is 11. You're going to get the same answer. So they're both valid ways to do it. As far as a decimal goes, 11/12 is approximately 0.917. So that would be okay. Or if we wrote it as a percentage, that'd be 91.7%. That's also okay. So lots of ways you could write that answer. How you feeling about that? The relative frequency histograms usually come up in the homework at some point, so that's why I like to do those ones. Most people are pretty good with the pie charts and different stuff like that, but if you have individual homework questions that you get stuck on, come see me during office hours. I'm happy to help you sort through that. If you can't come to my office hours, starting next Monday, drop-in tutoring in the library is going to open. All that information is posted in my Canvas page, so you don't have to remember anything that I'm saying. So my office hour times are there, and also the drop-in tutoring is that info is there. Yes.
On the topic of the Canvas page, were the other students who did not sign up for the class they're scheduled to added to the Canvas page?
They should have been. If they were not, I will take care of that today. I tried to add everybody, and it might have glitched, but I got pretty much everyone on there. So I will take care of from that list. Not that list. The list that's going around. I didn't get it back yet. Where's the sign-in sheet? Beautiful. Anyone need the sign-in sheet? Cool. Can you just pass that to the back? Just teamwork. Pass it to the back. Thank you. Thank you. All right. That was my first handout. Jen makes a lot of handouts though, so I have another handout. You ready for another handout? The other piece that I believe you started talking about today, and if you didn't, you'll start talking about it on Friday. Quartiles and percentiles. Did she do a formula that had a K in it? Ooh, I get to be ahead of schedule today. Nice. I think I get to be ahead of schedule. It's entirely possible I'm not doing what she's doing. At some point, someone will want to send me her notes. Did she send out her notes yet? Oops. Maybe one that's not separated. There you go. Did you talk about anything else today that you wanted me to cover? Did you say anything that you were like, what the heck? Usually the first few days aren't too bad. This stuff is where the math starts. So the handout I just gave you, it's where the math starts. Okay. Quartiles and percentiles. She's going to give you a formula. So I'm actually going to have you flip to page 2 since you guys haven't seen the formula yet. Normally I'm doing this and people have already seen the formula in lecture, but flip to page 2 so you can see the formula. The formula for finding percentiles for data looks kind of funky. It says I is equal to K divided by 100 times N plus 1. There's 1, 2, 3 variables in there, so that can feel intimidating sometimes, but each of the variables in statistics has a very particular meaning. So when we talk about percentiles, have you heard the word percentile before? Like in your normal lives? Usually percentiles come up when people have taken exams or different things like that, and people are like, oh, she placed in the 99th percentile. Parents love to brag about this. Oh, she was in the 99th percentile. What that means is that 99% of the data fell below that score, and 1% of the data fell above that score. So if your child scores at the 99th percentile, you're saying if you lined up 100 kids, your kid's at point number 99. And that there's all these other kids below your kid, and there's only maybe one kid above your kid. And so that's why people get very braggy about the percentiles. When we do things with statistics, often the percentiles we care about come from a really particular chart that you may or may not have seen in a past life. It looks like this. Anyone seen a chart that looks like that before? Who's never seen a chart that looks like this before? Yeah. When I was in high school, we didn't learn this, and then it became a thing when I went back and started teaching high school. Then they were like, okay, what did you guys call it? Some people learn this as a box plot, and some people learn this as a box and whiskers plot. So here's the box part. You can envision the box, right? These are the whiskers, like on a cat. So the end parts are the whiskers, if they call it a box and whisker plot. What this does, if you've got a whole bunch of data, if we want to know where the middle of the data is, it's this line here. The middle of the data has a special name, and it's actually not the mean, which is the actual true average when we're doing like adding up all the numbers and divide by the number of numbers. If it's the middle of the data, that's the 50th percentile. That has a different name. It's a special name. It also starts with an M. Do you know it? Median. Yeah, that's the median. The median is at the 50th percentile. It's the middle number. If we went all the way back here, this should be the smallest number. We don't usually call it the 0th percentile. We usually call it one of the extreme values or the lower value. But this would be like your starting place. And this would be like your ending place. This should be your biggest value. So this should be your smallest value. And this one should be your biggest value. Okay. The median is the middle value. So then we've got the lower end of the box and the higher end of the box. And those get special names. This one right here, this end of the box is called Q1. And this end of the box is called Q3, which you might be like, wait, we skipped Q2. And the truth is we didn't skip Q2. Another name for the median is Q2. We just don't usually call it Q2. We normally call it the median. But if you wanted to call it Q2, you could. The Q means quartile. And if I say quarter, there's 4 quarters in a dollar, or 25 cents each, or 25% of a dollar is in each of those places. A quarter is 25%. So this is the 50th percent. So Q1 is actually the 25th percentile. And so then what do you think Q3 is? 75th percentile. You got it. Okay. Now, all my people online are like, that was all on a chalkboard that we can't see. Sorry, people online. It's okay. At some point, I promise I'm going to draw these all out for you again. But in terms of percentiles, we actually can do more than just 25th percentile, 50th percentile, 75th percentile. If we use this formula, we can find any percentile we want. We could do the 63rd percentile. We could do a crazy percentile. We just need this formula. The I represents the position in the data. The K represents the percentile we're looking for. And the N represents how much data we've actually got right in front of us. Okay, so the easiest way for me to kind of talk through this is to show you some data and then work my way backwards. But that means we're doing the packet backwards. Do you feel okay doing the packet backwards? We'll keep flipping back and forth, but you'll be like, Jen, why'd you make the packet in this order? Really, we should do the packet backwards. Well, Normally she's introduced all this, so I don't have to do the packet backwards. But since she hasn't introduced it yet, I'm going to do the packet backwards. Okay. So the last page in your packet says, listed are 29 ages for Academy Award-winning Best Actors in order from the least to the greatest, or the smallest age to the biggest age, or the youngest person to the oldest person. That's important. When we do this, we have to put them in order from the least to the greatest. Okay? They're already in order for us, so you don't have to do that. How many of them are there? 29. Which of the variables on the last page is that? The I, the K, or the N? N, that's our N. So our N is equal to 29 in this problem. So I'm going to write that at the top so that I don't forget it. My N is 29. Very good. Okay. It says, find the following values. Find Q1. Q1, what percentile is Q1? 25th percentile. Okay, so Q1 is the 25th percentile. So in this case, our K is 25 for that formula that we're talking about. So there's only one more variable that was in that formula, and it's an I. The I is the position, and by position, they mean where in the list is the number. So this would be position 1, and this would be position 29, because there's 29 numbers. Is that okay? So what our formula pops out is the I. So I'm going to write the formula again. I'll put it up at the top. I is equal to the K, which is the percentile, divided by 100, times N plus 1. What pops out is the position. And so if I want the 25th percentile, here's how I plug everything into that formula. I'm going to say I is equal to, instead of K, I'm going to write 25 because I want the 25th percentile, over 100 times, and then instead of N, I'm going to plug in 29 plus 1. 25 over 100, are you okay with me turning that into 1/4? I'm just simplifying that fraction, 25 over 100 to 1/4. And then 29 plus 1 is 30. So if it helps, you can put that 30 over 1 so you can see how I'm going to multiply those out. I got 30 divided by 4. 30 divided by 4 doesn't come out to be a whole number. It comes out to be a decimal number. It comes out to be 7.5. Okay. So in terms of what just popped out, that's my I. That's the position. Okay. So the position is position 7.5. We can't actually go to position 7.5, but we can find position 7 and we can find position 8. And what we'll do is add them up and divide by 2. We'll find the average of those positions. So position 7. 1, 2, 3, 4, 5, 6, 7. Number 29 on my list here, that's 7, which means 30 is 8. So I'm going to take 29 plus 30. And I'm going to divide that in half. Now, I actually don't need a calculator for that because halfway between 29 and 30 should be 29.5. But if you put it into a calculator, I promise you'll get 29.5 out. Okay. This is the 25th percentile. So you use the formula to find the position. Then you go back to your list and find that position, and then whatever number is in that position, or maybe the 2 numbers that you take the average of, then that's going to be the number that's the percentile. Median. What percentile is the median? 50th percentile. Good. So that means that our K is going to be 50 in this problem. We're going to just plug everything into that same formula. So I'm going to say I is equal to 50 over 100 this time. My N is still 29, so we still got 29 plus 1 there. 50 over 100, are you okay with me writing that as 1/2? And then 29 plus 1 is 30, so I'm going to do 1/2 times 30. 30 divided by 2 is 15. This time we didn't get a decimal, so I actually just have to find what's the 15th number in the list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 47 is our median. So 47 is our median. Okay. Try Q3. See if you can do Q3 before I do it. Try Q3. What percentile is Q3? 75th. Yep. So you're going to do K is equal to 75. See if you can get the number before I get it. Anybody get Q2? I shouldn't have written Q2. What should I have written? Q3. Anybody get Q3? Did you get a whole number or a decimal for your final answer? Whole number. 67 plus 69 divided by 2 is asking what number is right in between 67 and 69. Did you get 68? Yeah. 68 is the third quartile. Beautiful. Okay. So we've got Q1 is 29.5. Q2, or the median, is 47. And Q3 is 68. This last part says the I, and it shouldn't say IRQ, sorry. Jen's got a typo. You got to fix it on your paper. IQR is the order it should be in, not IRQ. This is how we just make sure you're awake. IQR. This stands for the interquartile range. Interquartile range. That sounds scarier than it is. The interquartile range is actually asking, what does this box end point go to that box end point? So it actually wants the Q3 minus the Q1. So interquartile range is always Q3 minus Q1. Okay, well, we got the Q3. We said that was 68. And our Q1 we said was 29.5. So 68 minus 29.5 is 38.5. That's our interquartile range. So I'm going to pause right there and then go back to the start of the packet because now we've got enough stuff to fill in the beginning of the packet. So first page of the packet, if we go backwards, it says, to calculate quartiles and percentiles, the data must be ordered from least to greatest or smallest to biggest. Yep. Perfect. Q1 is the numerical percentile where blank percent of the data is less than this value and blank percent of the data is greater than this value. And so for Q1, this first number is 25% of the data is less than this value. So Q1 is the 25th percentile. So if 25% of the data is smaller than that value, what percent is bigger than that value? 75. So we're going to put 75 right here. And 75% of the data is greater than that value. Perfect. The median is the numerical percentile where blank percent of the data is less than that value and blank percent of the data is greater than that value. What should I put in each of those spots? 50 goes in both of those spots. Nicely done. 50% of the data. So with the median, 50% is below it, 50% is above it. Q3 then is going to be the opposite of what we did for Q1. 75% of the data is less than that value, which means only 25% of the data can be above that value. Awesome. And the interquartile range is a number that indicates Q3 minus Q1. So the next question is kind of like not an intuitive question necessarily, but it says, do the quartiles need to be observed data values? And what that means is, does the quartile actually have to be in our list of data values? And our list of data values were these whole numbers up here. Those were the ages of our Academy Award winning actors, right? But our quartiles, some of our quartiles, when we did our calculations for the Academy Award winning actors, we got like 29.5, but we don't have 29.5 on the list. So when they say, does it have to be an observed data value? The answer is no. It's okay for us to get a number that's not already on the list. So we're going to say, no, it doesn't have to be an observed data value. Okay. This next part is something you've probably heard of in the past life, but when we do box plots, we want like our smallest value to be here and our biggest value to be here, but then sometimes we have these values that are like weird. They're like way the heck over here, or maybe like way the heck like falling off the board over here. And we give those a special name. Weird data values. Do you know what the name is for them? Outliers, yes. Outliers are data values that don't seem to fit with the rest of the data. So like, when we make a box plot, we really want the data to be like 25% of the data falls here, 25% of the data falls here, 25% of the data falls here, and 25% of the data falls here. That should always happen because from here to here, the median, that's 50%. And from here to here, that's 25%. So each of these should be cut into quarters. But if we get a really weird data point, we're like, I don't know what to do with that. So in order for us to identify whether a data point is weird enough for us to call it an outlier, we have a formula for that. So the interquartile range, the IQR, is from here to here. And that's the middle 50% of our data. So what we do is we say, if a value is more than 1.5 times this IQR away from our lower Q1 or above our higher Q3, we call it an outlier. So that's what this part is getting at. It says the IQR can also help us determine potential outliers in data. A value is suspected to be a potential outlier if it is less than 1.5 times, so I'll put parentheses around it, the IQR below the first quartile, or more than 1.5 times the IQR. So I'm putting exactly the same thing in both blanks. Above the third quartile. So if I take the Q3 and I subtract this number, and the value that I'm looking at is even smaller than that, we call it an outlier. And if I take the Q3, so the third quartile, and I add 1.5 IQR to it, and the value I'm looking at is even bigger than that, then I would call it an outlier. But if it's within that range, we wouldn't call it an outlier. We'd say, it's kind of a big data value, or it's kind of a small data value, but it's not so weird that we would call it an outlier. Outlier is like a bad name. We don't want to call it the bad name until it actually deserves the bad name. Okay. All right, page 2. That's our formula page. There's not a lot to fill out on this page, but it's good to have. We'll have it filled in properly. So before we begin computing the percentiles, the formula that we have, I is the position of the data value, K is the percentile, N is the total number of data values given. So our formula is I is equal to K divided by 100 times N plus 1. In this formula, I talks about the position in the ordered data. Below, write how you determine the kth percentile for when the percentile is part of the data and when it's not. So if I is an integer, so when we did our calculation and we did our calculation for the median and it came out to be a perfect 15, all we had to do was count over to 15. We didn't have to do anything crazy beyond that. So if it's actually an integer, then I is the position of the data value at the kth percentile. Sounds like the best case scenario. If it comes out to be an integer, then that actually is the position. You just count over to that I. If it's 15, you just count to the 15th number. If I is not an integer, so when they say not an integer, they mean a decimal. So like say we get 29.4, then we got to take the 29 position and we got to take the 30 position and we got to add those up and divide by 2. So if it's not an integer, then choose the data value at the position just above and just below your I. Add add them up. And divide by 2. So we did that with our example, but it's good to have it written out. And then here's the thing we haven't done yet. So what we were doing is we were finding what is the 20th percentile, what is the 50th percentile, what is the 75th percentile. But I could ask the opposite question, and I could ask you to give a particular data values percentile. Or if let's see, so like it says now, what if we are given a data value and we want to find its percentile compared to the rest of the data? Well, we have this other formula, and the other formula is m is equal to x plus 0.5 times y divided by n times 100. Seems like a crazy formula. And we round it to the nearest integer for the percentile. Well, each of the values, they tell us what those stand for. We just have to fill in one of them. So x is the number of data values counting from the bottom of the data list up to, but not including the data value that you're trying to find the percentile for. Y is the number of data values equal to the data value that you want to find the percentile for. And n is what n always is. N is the total number of data values. Okay, so we haven't done an example of this yet, so we're going to go back to our example page and we'll do one. Okay. So we did the 25th percentile, the 50th percentile, the 75th percentile. Do you feel like you could do the 30th percentile and the 63rd percentile on your own? You're going to do exactly the same thing that we did, but instead of plugging in 25, you're going to plug in 30. And instead of plugging in 50 for the median, you're going to plug in 63, but it's going to be exactly the same. You do exactly the same thing for those ones. But the last one is different. The last one says, find the percentile for the data value 31. This is using that other formula we just got. So this is different. So if I didn't talk you through this one, you might be like, what? This isn't like anything we did. Correct. This is the other formula. So I'm going to write the other formula again. We've got m is equal to x plus 0.5 times y divided by n. I'm going to put that whole thing in parentheses and we're going to multiply by 100 when we're done with it. That's not too hard. Multiplying by 100 is just moving a decimal point over 2 places. Okay. Now, in this case, the x is the number of data values that are below 31 on the list. So I'm going to go back to our list and the number of data values that are below 31. Here's 31. So I'm going to cover it up because I don't want to include that one. I have 1, 2, 3, 4, 5, 6, 7, 8. 8 of those numbers are below 31. So that's the x. So in our formula, 8 plus 0.5 times y. Y is the number of data values that are exactly equal to 31. And in this particular list, we didn't have more than 131. They didn't give us like 31, 31, 31. If they did, we'd put 3 there because there'd be 3 31s. But we only have 131, so our y is 1. So we're going to say 0.5 times 1. Divided by the total number of data items, we had 29. That was our n for the problem. And then once we get that value, we're going to multiply times 100. So we have 8 plus 0.5, that's going to be 8.5 divided by 29. That's going to be 0.293 when I work that all out, and I'm going to multiply that by 100. Multiplying by 100 just means we're going to move that decimal point over 2 places. So it's going to be 29.3. It says round it to the nearest. Because it's a 3, not a 5 or bigger. So we're going to say this is the 29th percentile. Questions on any of that part? I know you haven't gotten that far yet. Do you want me to go ahead and fill in the 30th and the 63rd percentile so your handout is filled in? Yes. All right, so 30th percentile, we're going to have I is equal to 30 over 100 times 29 plus 1, because our n is 29. So that's going to give us 3 over 10, if I simplify 30 over 100, times 30. That's 90 divided by 10. 90 divided by 10 is just 9. So we're going to the 9th position on the list. So 9th position on the list, 1, 2, 3, 4, 5, 6, 7, 8, 9. I got the number 31. Ah. Okay, 63rd percentile. We're going to do I is equal to 63 over 100 times 29 plus 1. So 63 over 100 times 30 is going to give us 18.9. So 18.9 is not a whole number, so I got to find 18 and I got to find 19. I'm going to add those numbers up and divide by 2. So 18, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 is 57 and 19 is 58. So I'm going to take 57 plus 58. And then divide by 2. And that's going to give us 57.5. So that's the 63rd percentile. Right, all filled in. Okay. I think I'm going to go ahead and stop there so I don't get too far ahead of what she's doing. The next time I'm going to pick up talking about the box plot stuff. And then if anyone has any notes from her that you want to share with me, then I am happy to also include any of that stuff into the next one. Because right now I'm just guessing what she's doing. But if you have her notes, if you go in under Canvas to the discussion board, you can post them under there. Or if it's easier to send it to me as an email, that's also fine. But if it's in the discussion board, other people will go, oh, someone already sent it, and then I won't get 10,000 of them. But it doesn't bother me if I get 10,000 of them. So up to you. All right, if you didn't get a chance to sign the sign sheet, it's up here. If you need either of the handouts, they're up here. Otherwise, I will see you guys next week on Tuesday. Have a good rest of your week.